Hello everyone, welcome back to another video on organic chemistry. This time we are going to look at a revision on alkenes, which is the second chapter in chemistry O-level. So, what are alkenes? Alkenes are still hydrocarbon, just like alkanes was. Now, hydrocarbon means that they are going to contain the element hydrogen and the element carbon, and that's all. So, just like alkenes also are hydrocarbons because they contain only hydrogen and carbon. However, the difference between alkenes and alkanes are that alkenes are unsaturated. Now, what's meaning of unsaturated? Unsaturated means that they contains double bond. Now, where is the double bond? The double bond is between the two carbon atoms. Between two carbon atoms, you need to have a double bond. Now, how many double bonds? You need to have a minimum of one double bond for our syllabus. Next, we look at the general formula for alkenes. Now, what's the general formula? It is a formula that you will use to predict the number of carbon and hydrogen atoms that you're going to have in the homologous series. Now, this is a homologous series of alkenes. Here we will look at the number of carbon atoms, the name, the displayed formula, and what happens to the melting point and boiling point. This is a list of the different alkenes. We are looking at alkenes containing from 2 to 5 carbon atoms, and we are going to see as well what's the trend in the melting point and boiling point down the homologous series. First of all, we have to note, when we talk about alkenes, we see that in alkenes there is one carbon atom. The first member in the homologous series of alkenes contains one carbon atom. However, here it's different. In alkenes, the first member has two carbon atoms. Now, why is this so? If you remember, we said that in alkenes we need to have a carbon-carbon double bond. So, in order to have a double bond, we need to have a minimum of two carbon atoms, and then a double bond can exist between them. So, this is why alkenes will have a minimum of two carbon atoms. If alkenes had only one carbon atom, it cannot make a double bond with itself. Using this formula, when n is equal to 2, it's going to be C2H 2 times 2, 4. So C2, the formula will be CH2, CH2. Don't forget that this is a structural formula. The structural formula is an abbreviation of the displayed formula. So we have CH2, CH2, CH2. And this is confirmed when we look at the general formula. Let's look at when n equals to 3, the number of carbon atoms. N equals to 3, so it's going to be C3, C1, 2, 3. H is going to be 2 times 3, 6. So 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6 carbon atoms. Now, one of the important things which you can do to cross-check if the formula you have drawn is correct, you always have to know that carbons has to form 4 carbon bonds each time. 4 bonds, 4 covalent bonds. So let's look at this carbon. It has 1 bond, 2 bond, 3, 4. This one, 1, 2, 3, 4. And this one, 1, 2, 3, 4. Right? So then the compound is complete. And if we look at the structural formula, here it's going to be this first part, CH3, this part, CH, and this part, CH2. Coming to the fourth carbon atom, which is butene. This is a displayed formula. And finally, the fifth member of this homologous series, pentene, which contains 5 carbon atoms. Remember as well that alkenes, just like alkanes, are always going to start with a name, that is, the first member will have the name starting with meth, second if, third prop, but, pent, etc. In alkanes, as well as alkenes, they start with the same name. However, the difference is that in alkane the name ends with ane, whereas in alkene it ends with ene. So it's going to be ethene, whereas if it was a second member of alkane, it would be ethane. So this is one important way in which you can, just by the name, know if it is an alkane or if it is an alkene. The second way in which you can distinguish is just count the number of carbon atoms and the number of hydrogen atoms. If the number of hydrogen atoms is only twice the number of carbon atoms, this is an alkene. For example, this one, you have 4 hydrogen and 2 carbon. But if the number of carbon atoms is 2 times plus 2, like for alkanes it's CnH2n plus 2 times the number of carbon atoms, then it is an alkane. Finally, we are going to look at the trend in the melting point and boiling point. If you remember, when we talked about alkane, we said that when we go down through the homologous series, the molecules is getting more carbon. For example, this one has 2 carbon, 3 carbon, 5 carbon. Going down, it's having more carbon, and it's also having more of hydrogens. So when you're having more carbon and more hydrogen, it makes the mass of the molecule increase. When the mass of the molecule increase, the van der Waals force, which is the force holding the 2 molecules together, will increase. When the van der Waals force increase, the melting point and boiling point will increase down the group. It will increase. Which means that the melting point and boiling point of pentene is higher than that of butene, and butene is higher than that of propene. And this will have an impact on the physical state. For example, the members which will be up, the homologous series, will tend to be gas, whereas when you come down, you're going to get liquids, and as you go further down, you're going to get liquids with the which are progressively more viscous. But trend in flammability will be the same thing. The upper members will be more flammable, the lower members will be less flammable. The upper members will be more viscous, less viscous, whereas the lower members will be more viscous. In the next part of alkenes, we are going to look at isomerism in alkenes. If you remember, last time we saw isomerism in alkenes, and we defined isomerism as the existence of 2 or more compounds which have the same structural formula, molecular formula, but the displaced formula is different. Or it's even better to say that isomers are compounds which are going to have the same molecular formula but different structural and displayed formula. Now what does this mean? This means that if you take 2 compounds and they have the same number of carbon atoms, same number of hydrogen atoms, but just the way in which they are arranged in space, that is displayed formula is different, and when the displayed formula is going to be different, automatically the structural formula is going to be different as well. So this gives isomers. And if you remember, we also said that in alkanes, how we form isomers is by making branching. So you can have a straight chain, and then you can make a branch chain, so this becomes isomers. Now in alkenes, how do we have isomers? Yes, in alkenes as well, we can have branching, but most commonly in alkenes, we have isomerism in terms of the position of the double bond. We say that in alkenes we need to have a minimum of 1 carbon-carbon double bond. But where can we place this carbon-carbon double bond? You have to know that you can place it anywhere along the molecule. And by changing the position of the carbon-carbon double bond along the molecule, you're going to get different types of alkenes. Now of course, if the alkene is longer, there is more different place in which you can place it, then you're going to have more isomers. If you have only, like say, 2 carbon atoms, then the double bond can only be here, so you're not going to have isomers. Now consider these 3 molecules, all of which are isomers of pentene, because it contains 1, 2, 3, 4, 5 carbon atoms, so it's pentene. Pentene. Now, what's the name of this compound? If you notice, the double bond is at the terminal position. Now, in order to understand isomerism and to understand how are we going to name organic compounds, you have to start by putting numbers on the carbon atoms. This is the first carbon atom, so you call it number 1, number 2, number 3, number 4, number 5. Notice that the double bond is between carbon atom number 1 and number 2, so you're going to call it pent 1-ene. And you also have to know, instead of calling it pent 1-ene, you could simply just call it pentene. So when someone hears the name pentene, it knows that it's pent 1-ene and that the carbon-carbon double bond is at the terminal position, that is here. Now, what if the double bond was here? Would it still be pent 1-ene or would it be pent 5-ene? We still call it pentene, because if you take this molecule and you rotate it, automatically this double bond is going to be now on the left instead in the right. So just know when it is a terminal carbon atom, be it either on the extreme right or extreme left, we still call it pentene. Now let's look at this molecule. If we name it, this is the first carbon atom, this is the second carbon atom, this is the third, this is the fourth, and this is the fifth. It is between the carbon atom number 2 and number 3. We choose the lowest number, 2, so we call it pent 2-ene. And here you cannot name it, you cannot have any other name, you have to call it pent 2-ene. Now let's look at this compound. The double bond, the position of the double bond is changing. You have to remember, bear in mind, it's here in the first position, here in the second position. So this one and this one are isomers. But let's look at this molecule, right? If we start to count the number of carbon atoms, this will be 1, 2, 3, 4, 5. So it is between carbon atom number 3 and carbon atom number 4. So we can call it pent 3-ene. But what if we, instead of counting from right to left, we did the opposite. We started to count from left to right. Yes, it's possible. You can count from right to left or left to right. Doesn't matter. You just count it in such a way that you're going to end up having the least number of carbon atoms in the name. So let's start to count by here. So it's going to be 1, 2, 3. So if we start to count it from here, it's going to be pent 2-ene. So what name are we going to give it? Are we going to call it pent 3-ene or pent 2-ene? Remember, the rule is always you have to choose the least number. So pent 2-ene is a smaller number compared to pent 3-ene, so we call it pent 2-ene. And when we do this, we now find that this molecule, this one and this one, are not isomers of each other. They are the same thing. In fact, if you take this molecule here and you just rotate it, it becomes this molecule. They are the same thing, right? So only this one and this one are isomers. You can say pent-ene and this one are isomers, or this one and this one are isomers, but this one and this one, they are not isomers. So that's it concerning isomers. What you have to remember is alkenes can form isomers. It depends on the position in which you can place the carbon-carbon double bond. You can place it anywhere basically. At the terminal, at the center, doesn't matter. Only thing that's going to change is the name is going to change, or they're going to become isomers. But alkenes, the carbon-carbon double bond can occur anywhere, and the longer the molecule, the more places you can put it, the more different position you can have, and the different isomers going to become. In the next part, we are going to look at the sources of alkenes, which means that where do we get alkenes from? You have to know that alkanes or alkenes or any hydrocarbon, we obtain it from the soil. When we dig the soil down deep enough, we get crude oil, and from this crude oil, when we do fractional distillation, we separate the different fractions of the crude oil. We are going to get the different types of organic compounds, which we have seen in our first video. Now, at this level, we have to know where do we get alkenes from. Alkenes, we get it from alkanes. When we do extraction of crude oil from the ground, we are going to obtain large members of alkanes. Now, what are large members of alkanes? They are alkanes which contains a lot of carbon atoms, typically from 10 to above. So they are large members of alkanes. These large members of alkanes, they need to be cracked. Cracked means broken down to form smaller members of alkenes, hydrocarbons. Typically, when you're going to break down large members of alkanes, you're going to get smaller members of alkanes and alkenes and hydrogen gas. So remember, when you're doing cracking, cracking means you take a big molecule of alkane, you break it down, you're going to get smaller molecules of alkanes, smaller molecules of alkenes, and hydrogen gas. Let's take one example of this. If we look at this one, C10H22, it is a big member of alkane. We crack it. Now, cracking, it's very important to know in organic chemistry the conditions that we use to do the cracking. In order to crack this larger member of alkanes, you're going to need some conditions. Now, what are the conditions? For example, you might need a high temperature, high pressure, and you might also need aluminum catalyst. So under these conditions, these large members of alkanes are going to break down. Here it is forming a smaller member of alkane. This was a large alkane because it contains 10 carbon atoms. This one is a small alkane because it contains 5 carbon atoms. It forms alkenes and it also forms hydrogen gas. Okay, so that's it, how we do cracking. The next important thing we need to know is what is the importance for doing cracking. Now, large members of alkanes, they are not useful to us. We cannot use them very much because they are too large, they are too massive, they are too heavy, they are not useful. But smaller members of alkanes, they are useful. Now, where are they useful? For example, we can use it as a fuel, or we can use it as a chemical feedstock to make other compounds. So when we're extracting our crude oil from the earth, we're going to get large numbers of alkanes, but they're not useful. Instead, we need the smaller members to use them as petrol, fuel, or making organic chemicals. Therefore, what we need to do, we need to break them down, crack them down to form smaller members, which then is more useful and we can use it in a variety of other ways. This is why this is the importance of cracking. And the second importance of cracking is that it produces hydrogen gas. As you know, hydrogen gas is one of the important fuels for rockets, etc. And this is, for the time being, the main source of hydrogen. There are two main sources of hydrogen gas. First, we can do electrolysis of water, or second, we can do cracking of alkanes. In the next part of this video, we are going to look at the different reactions that alkenes undergo. There are many reactions of alkenes. We had seen that alkanes was not very reactive. This is because they have no double bonds, and there were strong carbon-carbon bonds and carbon-hydrogen bonds. But alkanes, you have to know that they are more reactive than alkanes, because they have a double bond. And if you remember as well, alkanes would only undergo substitution reaction because they were saturated compounds in which all the carbon atoms had already formed 4 bonds. However, in alkenes, they are unsaturated compounds. Alkenes contains a double bond in which you can add things to it. This is why alkenes are more reactive than alkanes. Now, therefore, alkenes would undergo addition reaction. But what can you add across a double bond? These are the 3 things which you can add. You can add a hydrogen, you can add halogen, you can add, or you can add one alkene and another alkene together and gives you polymerization. So let's look at each of the reactions step by step. In the first one, we're going to look at reactions of alkenes with hydrogen. As you already know, the difference between alkenes and alkanes is that alkenes has less hydrogen than alkanes. Alkanes are saturated, whereas alkenes are unsaturated. But if you take an alkene and across a double bond you add hydrogen, it will end up becoming an alkane. And this can happen. In fact, you take alkenes, you add hydrogen, under presence of nickel catalyst, it's going to give you alkenes. Alkanes, excuse me. And one example of that, let's take C2H4. You add hydrogen gas in it, it's going to become an alkane. So an alkane. Now, where do we use this? What is the use of this reaction in industry? When we take plant, for example, they give us oil. So if we take oil from plants and we add hydrogen in oil, it gives us margarine. So this is an important step in which we manufacture margarine using oil from plants, because margarine contains a lot of double bonds. So one way to understand this reaction is like you have carbon-carbon double bonds, you add hydrogen to it, the hydrogen will go and replace and break this carbon-carbon double bond and add it in the carbon-carbon double bonds. So we're going to have now 6 instead of 4 hydrogen bonds. The second reaction, so the second thing which you can add across an alkene is a halogen. Now what's a halogen? Halogen is, for example, chlorine or bromine. Anything like chlorine or bromine is a halogen. So if you take an alkene and you add a halogen to that, it becomes a halogenoalkane. And there's at this step one thing very important we have to know. For example, if we take an alkane and we add bromine in alkane, we had to this reaction carry out this reaction in presence of UV light, else it will not occur. And this reaction will take time. If you take chlorine, for example, and you add it to alkene, it will take some time, and the chlorine will slowly react with the alkanes to form halogenoalkane. However, if you take a halogen and you react the halogen with an alkane, if you take an alkene and you react it with a halogen, the reaction will proceed faster, and you don't even need UV light. So as soon as you add the bromine, it will get added across the double bond to become this one. You don't need any UV. So you can use it as a test to distinguish between alkane and alkene. Say for example you had ethane here, and you take a test tube containing ethane and you add bromine to it, you would see that bromine is a reddish brown. Reddish brown. So if you take alkane plus bromine, it will be a slow reaction because you need UV light. So very slowly the reddish brown color of bromine will fade away to give you a colorless solution. Colorless, whereas the bromine is reddish brown. But if you take alkene and you add a halogen, it is a fast reaction. Very quickly, the reddish brown color due to the bromine will fade away because the bromine will enter into the alkene. So that's a test to distinguish between alkanes and alkenes. Take both alkane and alkenes, add bromine, see and shake. If it is an alkane, the color will fade very slowly. If it is an alkene, the color will decolorize very fast. Now another example of addition reactions which you can have in alkenes, which is not mentioned here, is if you take an alkene, you add it with water in the form of steam, this alkene will become a alcohol. Okay? Say for example you take ethene, you add it with water, and the catalyst used in this reaction is phosphoric acid catalyst, you will get ethanol. Now, this reaction, since we are adding water, it is called a hydration reaction. A hydration reaction. And what is the importance of such a reaction? This reaction is used to manufacture alcohol, to make alcohol in industry. Other type of addition reaction which you can do is you can take an alkene and add an alkene with another alkene. It will give you a polymer. We're going to cover polymer in more details in the next segment. The last part, the last reaction that we have to look for alkenes is that alkenes, just like alkanes, you can burn it in presence of oxygen to form carbon dioxide, water and energy. However, note something is that it will produce lesser energy than alkanes, and it will form more carbon in the form of soot, which is a black smoke. Why will it form like that? Because unlike alkanes, it contains less hydrogen and more carbon. This is why it will form more soot, it will form less heat energy. So for these reasons, alkenes are not the preferred source of energy, used for energy in terms of fuel. We rather use alkanes instead of alkenes for fuel. Okay? So that's it concerning the reactions of alkenes. Very rapidly, just to make a summary, alkenes, unlike alkanes, have double bonds, so they're going to undergo addition. In the double bond, you can add a variety of substances, such as you can add water to make the alkenes alcohols. you can add hydrogen and make the alkenes become alkanes, or you can add a halogen to make it become a halogen-alkane, and you can use this as a test to distinguish between alkanes and alkenes. Or you can add several alkenes together, it will form a polymer, which we are going to see shortly. And finally, we can burn down alkenes to form carbon dioxide, water, and heat energy. We have finally come to the last part of alkenes. In the last part of alkenes, I'm going to explain to you in more details about manufacturing of margarine. Margarine is manufactured from vegetable oils. Now, vegetable oils, they are polyunsaturated hydrocarbons. What is polyunsaturated hydrocarbons? By now, you should already know that unsaturated hydrocarbon means the presence of double bonds. If they are polyunsaturated, it means that it contains more than one double bond. So, vegetable oil, they contain a lot of double bonds, so they are polyunsaturated. When you add hydrogen across these double bonds, this alkene is going to be converted, this alkene will be converted into an alkane. Now, in this case, it will become saturated hydrocarbon. Now, this saturated hydrocarbon is margarine. If you look at vegetable oil, it is oil, so it is a liquid. When you add hydrogen, you made it become more massive, and now it's going to become a solid, like margarine. So that's it for manufacture of margarine. And that's all that we have in our syllabus of O-level chemistry concerning alkenes. We will see you next time for another video. And don't forget to subscribe so that you can have all the videos that I'm going to upload on YouTube. Till then, see you. Bye bye.